Welcome to Monday of week 8 with Math 105. Hard to believe it's week 8. So, new topic this week. We get to leave behind describing data and move on to probability. Let me show you what's happening in our unfolding menus. So go down, Week 7, by the way, just to review, was not much happening. We had our test on Wednesday. There was no homework. Maybe you got some achievements done. Maybe you rested and caught up on other things in your life. I confess that I might have forgotten Saturday night study session. I don't even remember if I did or not. So if you were looking for me there and I wasn't there, I apologize. Since you all have my email and text, no one fussed at me. I hope it was okay. But anyway, now we're back to work. So week 8, when I look at it, we talk about likelihood, permutations, combinations, tree diagrams, and different kinds of events, complementary, independent, conditional, and contingent events. As always, we have our Get Help forum. We have a new textbook chapter. I'll talk a little bit about the pros and cons of this textbook chapter soon, but we are on a new chapter now. The activity for this week is up here. And as always, at the bottom corner, you can look at the answers. This week's discussion forum is about the difference between independent events and mutually exclusive events. Those words tend to be ones that people mix up until you've used them a bit. And Moodle doesn't know when you're done with this. So do what it tells you when you click on the discussion forum. It gives you clear instructions, but it won't check you off because it doesn't actually, it's not smart enough to know, did you actually follow those steps or not? And as before, if you're part of a study session or other outside study group, that counts as participating in a discussion also, and you can skip that if you want. I would recommend at least reading over your classmates' discussion forum answers, just to help in your brain clarifying independent events versus mutually exclusive events. I've started on the homework, but I haven't had time to finish yet because I've been busy with what else you'll see today. So if you go to the homework for part A, all the questions are there, but none of the multiple choice answers. So if you want to get started today, you can. I'm not holding you back from starting. The short answer questions are there also, but you won't be able to actually turn this in until I finish with putting things where the multiple choice answers are. Paula's weekly worksheet this time is not really a worksheet, it's just notes. So I also recommend looking at this. It's just sort of a summary of probability. So at the end, that's a good thing to look at and to make sure you're on top of things. There's lots of videos because there's lots of little bits and pieces to the topic of probability. If anything is confusing, feel free to use those. And there's only a few achievements that we haven't met yet. So there we go. Week 9 looks okay, but similarly, I don't have the homework yet. So you can't really jump that far ahead, even if you are speedy. Just as a recap, in week 10, it's our review week. There's nothing new that we'll study. We do have a Moodle forum question for week 10, which is just feedback about the class. Help me make it better for next time. So I will ask everyone, please, during week 10 or finals week, do that, even if you don't normally do the Moodle forums because you do studies instead. And the practice finals are not quite ready to be used, but all the problems you've seen before are there. So there we go. So that's our sort of schedule for finishing things up. Questions about all of that before we go on to other mathy things? Looks like everyone has put here in chat for attendance. Thank you. A bit earlier, it looks like Ashley asked, does anyone care to have a study session tonight at 10 o'clock in this Zoom link? So now that we're all done saying here in chat, you can reply to her and not have your answer lost in the flood of yours. Okay, our Jamboard has a few pages already presented. This is 17 and 21 from your midterm last week, which I should probably actually write that on it. So. Some people wanted to stay a little bit later after class on Wednesday, and we did these two problems together. Then this one I just put up as a bit of practice for us. Let me make this more shaped like the Jamboard. So there are two histograms. Two different children's art classes have the same number of students, but with very different ages. So try and use all the vocabulary we know to explain the ways in which these two groups of students are similar or different. So if you need to have done a problem in class for the achievement or just want to, then unmute and call out. We have lots of describing data jargon. How would you talk about these two different art classes? Should I be more clear? Someone give me just one of our jargon terms about describing data.
I'm sorry, can you repeat the question of what you wanted us to do?
Sure. What's just one of the jargon terms about how we describe data from last midterm?
Are you talking about like the categories or quantitative?
There's categorical versus
Quantitative.
quantitative. Which one are both of these? Quantitative.
I'd say categorical.
Quantitative.
These would be quantitative. The bottom axis are number lines. So what's more jargon we've learned?
Histograms or pie charts.
Yeah, what kind of chart is it? We had bar charts, histograms. Pareto chart. Pie charts. Which one or more of those are we looking at?
Histogram.
It is a histogram.
But also the Pareto.
It's a bar chart because we have bars. It's not a Pareto chart because
Oh,
they're
that's right.
from tall to short. How about averages?
Are you asking how we get the average or the mean?
I'm just wanting words and applying the words. So we had mean,
Oh, got it. Okay, so we got the mean, a median, range.
range was one kind of thing. Along with range went standard deviation.
Mhm.
Those were both more about the spread than mean and median.
Relative frequency.
Relative frequency was some good jargon. Okay, let's catch up to what we've just done. Frequency. So do these two data sets look like they have similar or different means?
I would say different.
What would the mean be for the left?
So, well, if we take the well, so we have to add this, all of these numbers, and then we have to divide by the number of numbers in order to get the mean. And so these numbers are 6 through 15. The other numbers are 2 through 18. So I guess I wouldn't be that different. I can go ahead and calculate it out.
We don't need to. And in fact, we
No.
really can't, because we don't know if this first marker here is 1 student or 3 students or whatever, right?
Oh, okay. I thought you would want us to take the 6, the 7, the 8, the 9, add those up,
Yeah.
and then.
Because we have more 7s than 6s and a lot more 10s. So we don't know how many 10s to add up when we're finding the mean. But we know how to find the mean just based on the shape. Where would the mean be on the left-hand side just because of the shape?
It would probably be, well, the 10 would be the median, right? Between the 10 and the 11.
The one that looks like a teeter-totter balance is the mean. So if this was to balance on a teeter-totter between 10 and 11, that would be where the mean is.
So.
The median would be sort of where it balances, but let's toss out the things on the very edge, which looks to be about the same. We're going to get rid of about the same number of things that are unusually high or low, and it will still be at about 10-ish. How about the group on the right? Where is its mean?
So the 18, so if you're taking the 2 and the 18, so it looks like it's probably right in between the about the 12.
That looks like it's gonna.
Is that too far over?
If I try and draw a teeter, oh, that's the wrong pen. If I try and draw a teeter-totter under 12, to me that looks like this side is too high.
A little too far. So then probably more like between the 9 and the 10.
10.5.
Something like that. Now this side looks a little heavy. I think it's about
10.5.
between 10 and 11 again. So the means look very similar. Are the medians similar? If we get rid of the high and lows for both, are they still going to balance at about 10 or 11?
Yes, but on the second chart, you would be getting rid of more than what you would on the other side.
When we look at the sorted list and pick the middle, it's going to be somewhere in this bar on both of them. Right? That's the other way we were saying. That's actually a better way. Don't think about balancing for median. Ignore what I just said. Okay, range. Which group has a bigger range?
The second chart.
The second chart, it goes all the way 18 minus 2 is 16. Which group has a bigger standard deviation?
The second one?
The second one, for the same reason that if we look at what's the mean, there are more things far from the mean. Whereas on the first chart, almost everything is really close to the mean. There's not much deviation that way. So the standard deviation is bigger when things are farther from the mean. The relative frequency, we could ask questions about particular bars. What is the relative frequency of this bar? It would be hard to find out. We'd have to measure the height of all the bars and then have the height of this bar compared to the total. And since our y-axis isn't measured with numbers, that would be unusually annoying work. Okay, well, except for me being confused, don't think about median as where it balances. It's where the middle thing is, which bar the middle number would be on. And I hope that was okay. This picture we'll get to today. I just wanted to leave it on the Jamboard in case writing on it was helpful. And then I wanted to take a quick break and do a story time with something from Peter Pan before we really start chapter 8. So, everyone ready for story time? I have this beautiful copy of Peter Pan. And is there anyone that's read the original Peter Pan other than me here? That must be a no. Okay, so if you haven't been told, the original Peter Pan is a very strange book all about why we love little boys, even though they are confused and wrong all the time and kind of annoying and rambunctious. It is not a book for children. It is a book for parents, especially moms of boys. And it is written with everything is all mixed up just because it is written the way children perhaps understand things. So the parents, for example, are Mr. and Mrs. Darling because the mom always calls the dad Darling. So that's what the kids think his first name is and things like that. So yes, Disney changes everything. They changed this story tremendously, but there's something that happens just on the second page that relates to our midterm. So I wanted to read just a little bit of this. So I stopped my fancy Zoom background because it seemed strange to read a book to you, not just like at my house. Anyway, chapter 1, Peter breaks through. All children except one grow up. They soon know that they will grow up, and the way Wendy knew was this. One day, when she was 2 years old, she was playing in a garden, and she plucked another flower and ran with it to her mother. I suppose she must have looked rather delightful, for Mrs. Darling put her hand to her heart and cried, "Oh, why can't you remain like this forever?" This was all that passed between them on the subject, but henceforth, Wendy knew that she must grow up. You always know after you are 2. 2 is the beginning of the end. Of course, they lived at 14, and until Wendy came, her mother was the chief one. She was a lovely lady with a romantic mind and such a sweet, mocking mouth. Her romantic mind was like the tiny boxes, one within the other, that come from the puzzling East. However many you discover, there's always one more. And her sweet, mocking mouth had one kiss on it that Wendy could never get, though there it was, perfectly conspicuous in the right-hand corner. The way Mr. Darling won her was this. The many gentlemen who had been boys when she was a girl discovered simultaneously that they loved her, and they all ran to her house to propose to her, except Mr. Darling, who took a cab and nipped in first, so he got her. He got all of her except the innermost box and the kiss. He never knew about the box, and in time he gave up trying for the kiss. Wendy thought Napoleon could have got it, but I can picture him trying and then going off in a passion, slamming the door. Mr. Darling used to boast to Wendy that her mother not only loved him, but respected him. He was one of those deep ones who know about stocks and shares. Of course, no one really knows, but he quite seemed to know, and he often said stocks were up and shares were down in a way that would have made any woman respect him. Mrs. Darling was married in white, And at first she kept the books perfectly, almost gleefully, as if it were a game, not so much as a Brussels sprout was missing. But by and by, whole cauliflowers dropped out, and instead of them, there were pictures of babies without faces. She drew them when she should have been totting up. They were Mrs. Darling's guesses. Wendy came first, then John, then Michael. For a week or two after Wendy came, it was doubtful whether they would be able to keep her, as she was another mouth to feed. Mr. Darling was frightfully proud of her, but he was very honorable, and he sat on the edge of Mrs. Darling's bed, holding her hand and calculating expenses while she looked at him imploringly. She wanted to risk it, come what might, but that was not his way. His way was with a pencil and piece of paper, and if she confused him with suggestions, he had to begin at the beginning again. Now, don't interrupt, he would beg of her. I have £1.17 here and 2 and 6 at the office. I can cut off my coffee at the office, say 10 shillings, making 2, 9, and 6. With your 18 and 3 makes 3, 9, 7. With 5, not, and my checkbook makes 8, 9, 7. Oh, who is that moving? 8, 9, 7. Dotton carries 7. Oh, don't speak my own. And the pound you lent to that man who came to the door. Dotton carry child. Oh, there, you've done it. Did I say 997? Yes, I said 997. The question is, can we try it for a year on 997? Of course we can, George, she cried, but she was prejudiced in Wendy's favor. Remember mumps, he warned her, almost threateningly, and off he went again. Mumps, £1. That's what I put down, but I dare say it'll be more like 30 shillings. Don't speak. Measles, 1.5. German measles, half a guinea, makes 2.15.6. Whooping cough, say 15 shillings, and so on it went. And it added up differently each time, but at last, Wendy just got through with mumps reduced to 12.6 and the 2 kinds of measles treated as one. Okay, all of Peter Pan. That's the most math there is in the whole book. Anyway, so I'm reading that because after midterm 2, I got a bunch of emails with people saying, I think I got things right when I'm trying to grade my work, but I'm rounding a little bit differently than what the answer key says. Does that matter? And the answer is no. That we probably, as all of the people here in this room, have never had a case where one of our real life decisions mattered about some little rounding error. We round it to the whole number or 1 decimal place or 2 or whole dollars or cents. And that's because in real life, we want to know something like, can we afford to buy this house? Or what kind of presents can I afford to get my kids for the holidays? Or should this business hire or fire another employee or something like that? And the rounding just doesn't matter. And when the rounding does matter, it's like Mr. Darling on page 2 of Peter Pan, where he just sort of makes things up until it comes out the way he wants. So rounding errors just are not a real life issue. If after grading your own midterm 2, you were worried, did I round right on this problem? It looks pretty good. It's just the rounding thing. That's not a sign that you're having a math issue. That's a sign that you have some emotional baggage from some previously abusive relationship. And let's call it what it is and not worry about it. You know, we won't judge you for having it, but it's not a math issue. So there you go.
I have a quick question to go off of that.
Sure.
So like when we do our tests and we're working on the financial part of like finding how much we can afford for a mortgage. And we use that little chart. I can't remember the name of it. So say that once we do the math for that and it's 18,500, so it's 18,500, usually 5 and over, you would round up to 1,900, but since we're trying to save money, could we round it to like 1,800? Would that make a difference? Because that's almost $1,000.
If you look at some of the early example problems on the website, then it talks about that there are times you want to under budget on purpose, so you don't round up and spend too much for cars and houses and big things.
Okay.
So yes, that is perfectly reasonable. Okay, that's why there's Peter Pan. I don't think he deserves a whole Jamboard page though, so I will erase that there. If you haven't read Peter Pan, especially if you are the mother of boys, then that is a strange book, but probably fun to read. Okay, while we're talking about books, let's talk about So if you click on our textbook, then probability is not actually that bad. We could describe it as being a math topic that's easy in the way that makes you want to beat your head against the wall. The reason it's frustrating is because it is usually presented badly. It's almost unavoidable to present it badly. There are so many different little pieces of jargon and terms and words that sound similar to each other in this jargon that it is very tricky to like lay out things on the table in a clear way and say, this is the path we will walk to get our nice introduction to probability. And the book does an okay job, but not a great job. What is very useful is looking at this textbook after you've seen the lecture notes and the lecture. I, of course, happen to like my way of arranging it better than this author's way. You can either agree or disagree. Please let me know. But both ways will be good to see. Just the nature of this material, the way the words work, not the math, but just the words and the concepts, then it's good to see two people explain it differently. So if you are someone that says, oh, there's a website thing here all about typicality, I'm going to look at probability, this is what we're about to do in the lecture. I like the way the teacher's website is more colorful and fun, right? Maybe you haven't looked at the textbook much yet this term. So this is the time, week 8 and 9, to open your textbook if you haven't before. It will be 10 times more useful now than it has been before. So there is your warning about the textbook. Don't ignore it. Maybe not start with it, but don't ignore it. Okay, and with that, I think we're ready to start. I'm gonna head to the top. There used to only be 6 things up here. So there's this new topic, typicality. And if you were to look at the top of it, it would have stuff that looks familiar. I've spent some time going through our describing data topic and begin preparing it for next term, whenever it is I teach this next. So you will see things that look familiar here, right? Things moved from the homework and so on, turning the frequency table on its side, making it into a bar chart, all the stuff that we've talked about is already. So categorical data versus ordinal data versus numerical data and so on and things like that. Relative frequency. So the beginning of this page is all the stuff we've done already. But we are now jumping to probability down in the middle of this page. If you look in between what I just showed you and where I jumped to, it's not finished. I haven't gone through all of this stuff and finished making it ready for next term. So if you just start at the top, don't be surprised when you sort of have this void of like an unfilled swimming pool and stuff stops happening. But when we get to probability, it picks up again. Okay, I wish again, as many times, that we were physically in the same classroom. I have a bucket full of these plastic spinners where you can put the spinner on top of a piece of paper and turn any little picture into a spinner. But I can't. So you just have to kind of picture that you have a plastic object that you can put on top of these and make a spinner. I'm going to first ask about what makes this game fair. So in our simplest example, then this is sort of boring and fair. If we were to put a spinner here and spin it around, that's a terribly unstraight spinner. Oh, I have to use my... Then why would we think this is a fair game? We're assuming you like earn $1 or pay $1 based on where the spinner lands.
You have a 50-50 chance.
You have a 50-50 chance. Unless the spinner was not fair, you would expect it to land on the plus and minus equal amounts. You might get a run of good or bad luck. Maybe you were incredibly lucky and got +1 5 times in a row. But if we did this all day long, you would expect that overall you would win as much as you lose. Okay, how about the next one? Now we'll make you think. I want this to be fair. Where will I draw my lines so that there's a +2 part of the pie and a -1 part of the pie? I will give you, for example, the wrong answer. If we drew our lines like this, that would be dreadful. We'd almost always be earning money, and we would be earning more money than we lose if we did get a -1. So this is not a fair game. This would bankrupt the carnival very quickly if they offered this to us. So
Wouldn't it just be down the middle, just like the other one?
down the middle. If that's where the line was, let me put my spinner a different color. So if that's where the line is, then half the time we will get a +2 and half the time we'll get a -1. So overall, we're going to rack in money. What else could we do instead? Straight down wasn't the right answer.
Well, I mean, if you have a +2 and a -1, then you have to compensate more on the -1 side, right? Because you essentially have 3 more with the +2. But where to draw that line? I mean, I want to say a third, but you just drew a third and that wasn't correct. So would you hyper compensate by giving a little bit more?
If we drew it like that, then it's true that there's sort of a dotted line going this way, right? Here we have thirds, 1/3, 1/3, 1/3. And this will work. That only a third of the time will my spinner land on +2. Twice as often, it will land over in this twice as big section. But I will only lose half as much. So overall, I am going to be even. Does that make sense now? For some people, these gray dots make it clearer. For some people, that makes it less clear. But that's where I want to draw my lines.
So in other words, it's important to look at what the numbers are there because that's going to help us decide on where it's going to be even at.
All right.
Okay.
Okay, another one. Now we have +3 and -1.
Would that one be like 1/4 of it?
Mm-hmm.
3 and the 1.
So I'm going to make quarters, but then this is all just like one section for -1, right? So a quarter of the time I will get $3. 3/4 of the time I will lose $1. And those end up balancing each other. Some people will enjoy it if I label this 2/3 instead of 1/3 twice. This side is a positive 2/3. This side is a negative 2/3. This is a positive 3/4. This is a negative 3/4. I'm winding up multiplying these things. Another way to say it is you take the two numbers that you started with, the 3 and the 4, add them up, and that's how many pieces you need to chop the pie into. So far, so good. Okay, if you really want to test yourself, come back to this online lecture notes. Here is one that will have 3 spaces for the spinner to land, a +2, a +1, and a -1. The -1 will have to be the biggest to balance out the others, but how big to make it? And you can see your answer there. So we're trying to start thinking about probability. That was our fun warm-up. And unfortunately, it gets less fun. As I mentioned before, there's just a lot of words. And the math isn't hard. It's sorting through all the words that's frustrating. So I will go slow and careful. We have lots of time, and try and organize these words on the page and in your brain as well as I can. And the first word we're using is just probability. Oh, by the way, is my font a good size before I just start reading out loud to you? Holler if it's not.
Yeah, it's good.
Good. Okay. The probability of a situation happening is the ratio of our desirable outcomes to our total outcomes. And by tradition, we write these as unreduced fractions, or we change them into a percent format. And basic probability problems are all about counting. There usually isn't a formula to help us. So the most classic example from math textbooks going back forever is rolling 2 dice and adding them up. Did we have a 2 dice chart already in this class? I can't remember. I've been staring at this for so many hours the past week and a half. I don't remember what we've actually talked about. Have you seen this chart before at all?
That chart is new to me.
New to you. Okay, good. So let's take this chart, stick it on the Jamboard. That's the page with books, right? No, that's the page with books. Okay. So this isn't hard. We all know how to count. So let's just make up a problem. Probability. The sum is less than or equal to 5. So I have to take my chart and I will highlight the ones that work. 2 works, 2 and 1 and 1 and 2 both work. 3 and 1, 2 and 2, 1 and 3, all of those work. 4 and 1, 3 and 2, 2 and 3, 1 and 4, all of those work. So how many did we get overall? That we just shaded in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 that work. How many are total on our whole chart?
$36.
Yeah,
36.
36.
Oops. So I could just be done. That's a good answer. Or if I wanted, I could say that 10 divided by 36, whatever that is, as a decimal, 0.27, repeating. And is acting. What we don't normally do, unless you work in advertising, is reduce this. It is true that this is the same thing if I divide top and bottom by 2 as 5 over 18. But there's nothing in the situation about 5 over 18. It's not like 5 things worked out of 18 things. Right? The real life situation had 10 things that we counted the real things and 36 things that we counted. If you reduce your answer for probability, then you're imagining a different situation. So There we go. Okay, questions about that example? Okay, in the lecture notes, we use the highlight green ones because you couldn't actually watch me highlight something. When rolling 2 dice, what's the probability that the sum is 7? So how many greens were there? 1, 2, 3, 4, 5, 6. So we could write it as 6 over 36 or change it to 16.7 or 17%. When rolling 2 dice, what's the probability the sum is 10? We'd have 3 pink ones out of the 36, or find the percentage for 3 out of 36. If dice seems a little cliche, we can talk about gumball machines. Imagine there is a gumball machine with equal colors of all these gumballs. Bigger. And to be polite, I've already made a nice colorful chart of all the ways you could get 3 gumballs out of the machine. You could get red, red, red. You could get red, green, red, and so on. Just like with dice, rolling a 5 and a 1 is a different thing than rolling a 1 and a 5. In this table of gumballs, getting a red and then 2 greens is different than getting 2 greens and then a red. Is that okay with everyone? Someone in chat says it looks like phenotypes. Yes, genetics does this kind of thing. So my question is, if I get 3 gumballs, how likely is it to get at least 1 blue gumball? So again, write it as a fraction and write it as a percent. Don't reduce your fraction. Try this before I do it, just to make sure you're understanding things. When you get an answer, put it in chat and call out. So let's count how many work. How many have at least 1 blue? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 18 of these work with at least 1 blue. Did I miscount any?
It looks like there's one more in the middle
Oh, there's
row.
1 more.
Yeah.
Good. Okay. Probability is a little bit like where is Waldo? Can you count things right? How many are there total? Well, 3 and 4, 5, 6, 7. 3 times 9, so 27. That's my fraction. I don't happen to know what 1926 is. So up 7%. Questions about that one now that we've seen it? No questions. Okay, on we go. Notice that the probability event that is certain to happen is 100% or 1. The numerator and denominator of the fraction will be the same. Event is impossible, probability is 0. The numerator on top of the fraction is 0, none of them work. And for anything, it must be between 0 and 1, between 0% and 100%. As a little bit of jargon, we normally use the word desirable outcomes or desired outcomes. I've been using work, 19 work, 10 work, because we actually have 0 emotional investment in this. Do we really desire them? No, but just traditional in the math literature, instead of calling them working outcomes, we call them the desirable outcomes. They're the ones that problem cares about. Okay, odds. New vocab word. The odds of event is another ratio. It's the desirable outcomes to the undesirable ones. And because of another tradition, odds are usually written as a reduced fraction, and they're not changed into a percent format. So let's go back to our original thing here. Oh, where was it? That one. I'm going to copy that so it's saved. And instead of probability, now we're going to ask about the odds. So it's still true that 10 of them work, but now what we're going to count carefully is not the total, but everything that we didn't count before. So this area here. So there were 36 before. If I take away the 10 that do work, then I get 26 that don't work, that are undesirable. So our new fraction is not 10 over 36, but 10 over 26. And because it's odds, I do want to reduce it. Some people also write odds with a colon, especially if you are betting on horses or taking an SAT test. And some people just use the word to. Everyone okay with that? Any quiet people? Okay. So again, we have the problems from the highlight diagonals about 7 and 10. What are the odds for it being 7? There were 6 of them that were green. So that means that 36 minus those 6 is 3 that were not. So 6 to 30 becomes 1 to 5, and so on. try and do these two more problems about odds for the sum being 10 and the gumballs to see if you notice that if an event is certain, the odds will be 1 to 0. The always happens to the never happens. And if it's impossible, the odds will be 0 to 1. And odds can have any number. They don't stop at 1 or 100% like probabilities. A lottery can have odds of 1,000,000 to 1 without any stretch of the imagination. So two similar ideas, but different jargon. Probability, the denominator is the total number of things in the whole realm of possibilities. Odds, the denominator is the ones that fail our condition we're looking at, the ones that are undesirable based on that problem. Any other questions? Okay, moving on. More jargon. Let's keep talking about our dice. The individual ways the situation can happen are called outcomes. So rolling 2 dice and adding them up, there were 36 different outcomes. The collection of outcomes we can call an event. So summing to 7 is an event that had 6 different green boxes, 6 different outcomes as part of that one event. We could list the 6 outcomes that make the event of rolling a 7 if we wanted. We could roll a 1 and a 6. We could roll a 2 and a 5, and so on. We can list them like that because they are real things that happened in real life with a dice. You could take a picture of it. We can't list the event. We can say its name is the sum is 7, but we can't use our cell phone camera to take a picture of all of the ways that one pair of dice could roll a 7. We'd have to pick up the dice and keep rolling them. That would take a video, not just an image. If an event has only a single outcome in it, like the only way to roll a 12 is to get double 6s, we call it a simple event. Simple meaning that there's just one outcome that we are renaming as an event. Many events contain several outcomes, and we'll call them compound events. So rolling a 10 or more, rolling a 5 or less, there's lots of ways that could happen. Even the sum being 7 is a compound event because there were 6 different green boxes that would make the sum of 7. So when I say that a sum of 10 or more is a compound event, it's not because it says or more. It's because there's more than one box that makes it happen. We could say the sum is 12 or more, and that would still be a simple event because you can't get anything other than the one box of 12 that does that. Everyone okay with simple events and compound events? Okay. I also need some more jargon because like the phrase, all the different ways this thing can happen, that takes too long to say. So the complete group of all the events is called the sample space. The sample space for rolling 2 dice has 36 ways it can happen. Now we have a nice short thing that we can talk about. I'm not sure why all of these phrases, by the way, have 2 words. Could be more efficient with our jargon, but gamblers didn't really care long ago. In this picture, I've colored the diagonals that if we just care about the sum, our sample space has $11 events. So this is a picture showing sample space has 11 events. Oops, has 11 events. There's the rolling a 2, rolling a 3, rolling a 4, and so on up to rolling a 12. It's also true that this sample space has 36 different outcomes. And if sentences like that seem annoying right now, then if you were to be actually doing some practical application of probability, you would appreciate having words that let you separate the event from the outcome. But right now it probably seems like people throwing jargon at you for no good reason. Everyone okay with this slide? Ready to move on? Okay, more jargon. Notice that real life situations can have many different sample spaces. We could ask lots of things about the sum. So this slide right here, the sample space was about adding 2 dice together, but we could do things like, do we roll an odd number or something, and just change how 2 dice works. Notice that events can overlap. If we ask, what's the chance of rolling 5 or more? That overlaps with what's the chance of rolling 9 or more. The 5 or more is a bigger area that overlaps the 9 or more area. Many real life problems involve sample spaces that are completely covered by 2 non-overlapping events. So we call these complementary. You've seen that word already before. It shouldn't be new. This is why we introduced it to you before. Either we roll a 7 or we don't. Either we roll an odd number or we don't. They are complete because that's all the ways it can happen. And they're exclusive. If you get one event, you don't get the other. There's similar jargon when, whoops, that should be 2TWO. Let me fix that real quick. 2 events, okay. Have no predictive effect on each other. When I roll 2 dice, what one die rolls doesn't affect the other. But in contrast, the weather in 2 nearby cities will have a predictive effect, because if it's raining in Springfield, it's probably raining in Eugene, or it just was, right? Events that don't contain predictive information about the other are called independent. So complementary means that they are 2 ways to share the sample space. It's either this or that, can't be both. Independent is different. We don't know how much these things overlap at all. It's just that if one happens, it affects the chance the other does. So if you need some cute little story to help you remember that vocabulary, complementary versus independent events, by the way, Strictly Ballroom is a wonderful movie. If you haven't seen it, you should. Whenever slightly sleazy Sam goes to a dance, he randomly tells half the women he dances with that they have pretty eyes. The events he says I have pretty eyes and he does not say are complementary, although neither is genuinely complimentary. So either he says it or he doesn't, can't do both, and he either will or he won't. There's no third option. The events he says I have pretty eyes and he says my best friend has pretty eyes, they are independent. He doesn't realize you two are friends. It's going to just be completely random for your friend, whether or not he said it to you. Everyone okay with complementary versus independent, at least at the moment? There's a great chance that as soon as class is done, this will leave your brain and you'll have to come back and look at it again. That's not unusual, don't feel bad. We're almost done. A little bit more jargon. When events are not independent, we can talk about how much they are conditional on each other. How much the probability of one event changes if we know, maybe we measured it and it happened, or maybe we're just assuming for the sake of the problem it happens, that the other thing did happen. An example of conditional events involves home pregnancy tests. They very seldom give false positives, but they commonly give false negatives. You can follow the link if that's news to you and you don't know that. The table below summarizes a study in which 900 women were asked to use a home pregnancy test, but then they also used a completely reliable blood test at a doctor's office to double check. So let's put this on the Jamboard. The fact that we're looking at a contingency table isn't news. You've used these before. This is why we talked about them. Now we are simply framing the same kind of thing you've already done on the midterm, but making it a probability problem just because of the context. So not new math, just new jargon. If we picked a random participant in the study, and remember that there were 900 total if we add up these numbers, what was the probability that the person was pregnant and got a positive home test? Somebody tell me what to do on the board.
Okay, so you want to know, say that answer or that question again, please.
Sure. What's the probability that the person was pregnant and got a positive home test? We're just picking one random person from the study and wondering about them for some reason.
So it would be the 322, wouldn't it?
It
Or
is.
positive.
So we're doing part divided by whole.
Mhm.
So 322 were pregnant and had the positive home test. And the whole is the 900. So whatever that is, about 36. Are so good? Okay, next, what's the probability that somebody is pregnant given that the test is positive?
Well, if you're looking at the part, so what is the probability of being pregnant, given that the home test was positive? And so pregnant, not pregnant was 3, so 322 were pregnant. So that would be, God, I am just, my brain is not working today. It's just
You're so
not
sorry.
happening. So, okay, so I can do this. So, so 322 women experienced a positive home test. And the question is,
No, they didn't. 322 were pregnant and had the home test. What's the total number for home positive test?
for a positive test was 322.
No,
No? Okay.
it's just the pregnant ones. There's these ones here.
Would it be 325?
325.
There you go.
You were on the right track, Marjorie.
I'm just going to start talking and thank you for the help.
Your courage is appreciated. Okay, so the whole for the pregnancy test tested was positive is the 325.
Okay. So 322 divided by 325. 99%.
99%. So as you can see, just looking at the top row, there aren't very many false positives. If it says positive, it's pretty good at knowing that that's really true. Okay, keep going. Last problem. I need to cover up that part. Okay, now we're asking what's the probability of being pregnant given that the home test was negative? So again, this was 325 and 575.
I'm just gonna go on a limb. Is it the 322 divided by the 298?
No,
No.
no.
Then would the part be the 277?
The 277 is the part. That's the group that is pregnant and home test negative.
Divided by 575.
And all the negatives are 575. The total for the negatives is 575. So 0.48, about. So there's a whole lot of false negatives. If you get a negative result, it really doesn't tell you any better than a coin flip what's happening. And of course, since we're talking about something medical, then this isn't actually true for any particular person. It's just that overall, people's body chemistry changes so much from person to person that no one has been able to make a good home test that avoids false negatives. Now, you can't avoid the false positives entirely, but when you design the test, they have to say, which am I going to? Let's pick the types of body chemistry to detect that avoids false positives, because that's much more problematic to have happen. Okay, anyway, there we go. Some events only happen if another event for sure happens. This is like the most extreme type of conditional event, and we'll call it contingent. And that's our last vocabulary word. And it's easy to brainstorm contingent events. I only eat birthday cake at a birthday party. I only climb trees when I'm outside, right? We can make stupid contingent events all day. Okay, that was an incredibly dense amount of jargon being barfed on you. Questions about any of those words you've now seen? Again, if you are a normal math student, this will all sort of make sense now, and then 3 hours later after dinner, when you look at the homework, you'll have to look at this again because it will have run away from your brain. That's okay, it will eventually stop.
Can you just show us where it's at on the website, like about the top?
Yes, and I'll send a link to. You go to the top with the kids, that's the typicality section, and then you go down in the table of contents to probability. Okay, more jargon, surprise, surprise. Most dice games ask the players to pick up the dice each time they roll. There's an official name for that. It's called an outcome with replacement. It doesn't matter what anything happened earlier, what the dice rolled previously, because we're going to pick everything up and re-randomize before the next roll. So let's do an example together. And I apologize, by the way, as you noticed, some of these examples have problem numbers, some of them don't, some of them toggle the answer, some of them just sort of show here. It's all just because I put this together over the past week. I should say thank you to all of you, by the way, for doing the type of midterm that you grade your own midterm. I would not have been able to make a nice lecture for today if I had spent hours grading your midterms last week. So good job, teamwork. Okay, someone makes a small deck of cards with only the ace through 10 of hearts. So here's that top picture. Those are the 10 cards we're dealing with. The game is that they shuffle and reveal the top card. Then they put that card back and reshuffle, and they again reveal the top card. What's the chance that both of the revealed cards are odd numbers? And we're going to consider ace to be odd. So here I've sort of put in green the cards that are odd, so half of them. Questions about the block quote? Questions about what game we're playing with cards? So our outcomes are pairs of cards. They can contain duplicates. If we wanted to, we could list them, double aces, ace and two, two and ace, and make a chart just like our dice had up above. But that would be a big chart, 100 different boxes. I don't want to do that. Our events are pairs of odd and even. And that's easier. We can just list all four of them. Even then odd, odd then even, and odd then odd. We need to keep track that even then odd and odd then even are different outcomes, different events, even though it sort of looks the same at the end of the day. Because we're just taking a card with a 50-50 chance of it being odd, then all four of these are equally likely. Even then even is a quarter, even then odd is a quarter, odd then even is a quarter, odd then odd is a quarter. So the one we want is this one here, odd and then odd. So it's only 1/4 or 25% that were in this box of our table. So that shouldn't surprise you. When I asked the question the first time, what's the chance of getting two odds? You probably thought 1/4 anyway. So far, so good. Okay, now is where it gets annoying in a kind of hurt your brain way. Most card games, however, ask the players to leave certain cards face up after shuffling and revealing the top card. You don't take cards out only one at a time and shuffle each time. So the official name for that is outcomes without replacement. We are not replacing the first card we set down on the table face up. It does matter what that is, because then we know the rest of the deck doesn't have that card anymore. This is a different situation, very slightly different, but different. So now we have a very similar game. Someone makes a small deck of cards with the ace through 10, same picture. But now when they shuffle and reveal the top card, they don't put it back. For example, if they drew the ace, what they would have left is just these 9 cards at the bottom, because the ace is on the table. Then they're going to reveal the next top card. And what's the chance that both of the revealed cards are odd numbers, with ace being odd? So it's almost the same problem. They're just leaving the first card on the table. Okay with this so far? Our outcomes are the same kind of thing. They're pairs of cards, but now they can't contain duplicates. So if we list them, we can't have double aces anymore. If we have ace and 2 and 2 and ace, that works. We wouldn't have 2 and 2 anymore, and so on. The events look the same. We either get even then odd then even, and odd then odd. But it's actually going to be more helpful to not write them this happens first and then this happens second. We're going to do reverse chronological order. And this is an important thing for what happens later on in the term. So this is why we're looking at this. We're going to say that maybe we had an even happen after an even. Maybe we had an odd happen after an even. Maybe we had an even happen after an odd. Maybe we had an odd happen after an odd. And why do I want to reword that? We'll see in a moment. So consider the event named odd after even. The probability that the first card is even, that's the even part, is 5/10. Half the cards were even after we shuffled the first time. But then the deck only has 9 cards, of which 5 are still odd because we just removed an even card. So in this picture, it was a 2. We don't know it was a 2, but whatever it is, now we have 9 cards and 5 of them are odd. So in this box, odd after even, the chance of the odd after the even is 5/9. It's not 50-50 anymore. So we're asking, what is 5/9 of the chance that the first card is even? That's this odd after even. And that makes more sense in English to say, what is 5/9 of the chance that the first card is even? It's awkward to try and phrase it chronologically instead of reverse chronologically. So the chance the first card was even was 50-50. So what's 5/9 of 5/10? Multiply across the top. 5 times 5 is 25. Multiply across the bottom. 9 times 10 is 90. And we can do the same thing for the other 4. Even after even, 4/9 times 5/10, and so on. So check these when you get home. This is a great review. We did this box together right now. The others are exactly the same, just slightly different. So this again is the table we care about, odd after odd. And it was 20/90, which is about 22%. So if we leave the first card on the table, the chance of our getting 2 odd cards goes down by 3%. And for most people who haven't done probability or gambling, that seems really strange, that just because you leave the first card down face up on the table, the chance of getting 2 odds is different. So if this hurts your brains, meditate on it at home more and see if you can have it make sense. I would even recommend taking a deck of cards and taking out maybe 4 cards instead of 10 and just doing this a few times. Because if your deck is small enough, if it's just the ace through 4, then you can actually see that change in probability happen much easier. Okay, again, I'm checking in because that was even more jargon.
No, I think you just nailed it. Just like you say, right now it's kind of like a slap in the face. We'll think about it. I watch the videos a couple times because that always helps me just to review material. So as I've already demonstrated, my brain is not working well today. So I'll definitely be doing a review of this one a couple times.
Okay, again, look at the official PDF textbook too. The videos are great, but the textbook is nice because you can scroll as slowly as you want. The videos tend to rush you a little. So do both. Okay, if we do very little Wednesday other than repeat some of this with more example problems, that's fine. I'm going forward now just because some of you will want to look at the homework and yeah. By the way, we finished all for 8A. So if we look at that, then when rolling 2 dice, what's the probability the sum is 8 or more? What are the odds the sum is 8 or more? You can do that. We just did this before. Here's a table about Lyme disease. It looks very similar to the one we did about pregnancy tests and questions about it, false positives and false negatives. There's a restaurant that surveyed 30 customers about breakfast, asking them about their favorite sandwich and favorite beverage. I'm not sure that number is actually correct. I will have to double check. So all of these add up to 30. 3 plus 9 plus 4 plus 9 plus 2 plus 7. Nope, I will get rid of that real quick. Okay, now it doesn't say 30. So what's the probability of this or that? So same kind of thing we did. And that's all of the 10 problems. So you are able to get the first half of the week's homework done doing very little other than counting things. Hopefully it will be a refresher of jargon, but no one is going to pop out from behind a tree and say, what's the difference between conditional and independent events? So
I have a question about number 1 on week 8 activity.
number 1, okay. I will look there, but I'm not going to promise that that's what I want to do right now.
Okay.
So activity number 1. Yep, we haven't done that one yet.
Oh, okay. Then that, I guess then that answers my question, because I was going to say that's a lot of writing each one out. What's easier way to do it?
It is, but we're about to do this. So thank you for that beautiful segue. You will collect your bribe later. Okay. So actually, let's look at that right now. Why not? As long as it's here. The local pizzeria offers 2 choices of pizzas, supreme or vegetarian, 3 choices for sides, chips, salad, or coleslaw, and 4 choices of drinks. I have to pick one of each for my meal. How many possible ways can I do this? So this is a good follow-up thing, that for 2 dice, we could draw a table that had all of the outcomes, all 36 outcomes, and even all 11 of the events, the sums, the 11 different sums. When we got a little more complicated with a deck of 10 cards, I didn't want to draw all of the outcomes. Drawing out 2 and 3, 2 and 4, 2 and 5, that would take too long. Instead, I just drew the 4 different events that I cared about and talked my way through it. But there are certainly problems where I don't even want to draw all the different events. There's just too many combinations. So what can I do when drawing tables is not the right thing? So, ready to figure that out? Okay, the previous example with cards, where we put 2 cards down, makes me uneasy. And I agree that the situation has an end result, what I called the overall sample space with 4 options: even after even, odd after even after odd, and odd after odd. But when I use the English verb sample in daily life, it means to randomly take one time. Like when I sample chocolates, that means there's some bowl of chocolates and I reach in once and take either a chocolate or a pinch of chocolates, but I don't get to reach into the bowl lots of times. I wouldn't say I sampled the chocolates then. I'd say I'm helping myself, or I'm eating the chocolates, or I'm picking out on chocolates. Sample would seem the wrong word if I reached in several times. If I sample some music, then I would listen to each song briefly. I wouldn't normally cycle among the songs the way I use the word sample. If I'd listened to the songs more than once each, I would say I'm comparing them, or I'm evaluating my mood, or I'm deciding what to listen to. To me, the word sample, as it's normally used in English, means that I pick one thing. So talking about a sample space when I turned over 2 cards seems kind of odd, because we did 2 things. So just a little heads up about that. My brain would more naturally wish that whoever invented this jargon would say we have 2 active sample spaces. The first one where there were 10 cards in my hand, and the second one where there were only 9 cards in my hand, because one was down on the table. And if your brain works like that, then this will make you happy. So here are 4 books that a toddler owns. As long as I seem to coincidentally keep mentioning books, if you don't know the alphabet room and have a toddler, that's a wonderful book. Or if you ever have to get a baby shower gift for people. The others that you probably have heard about if you have kids. Anyway, like most toddlers, she is fascinated by putting things in order and making combinations and patterns. So in how many orders could she put these 4 books on her shelf? What we don't want to do is try and draw the whole table. So instead, let's think carefully. We'll pick out the first book to put on the shelf. There's 4 ways to do that because there's 4 books on the floor. So we have 4 choices so far. Then we pick the second book to put on the shelf. And the current sample space then has 3 options because there's 3 books on the floor. 1 we've put away already. So now we have 3 more choices. We're up to 4 times 3 is 12 different ways to put 2 books on a shelf. When you put the third book on the shelf, there's only 2 options left. 2 books on the floor because 2 are on the shelf already. So now we multiply by a times 2 and we're up to 24 different ways. And at that point, there's only 1 book on the floor. We have no more choices. It just goes on the shelf. So we're staying at 24 different ways. We could draw a tree about the 6 choices that follow if we first picked the alphabet room. So I'll go back to where this tree was on the Jamboard. No, I won't because it has more writing on it. Never mind, I'm distracted. I will copy this and move it there. So we've already made one of our decisions and put the alphabet room on the shelf first. We would have to draw different trees to start with a Goodnight Gorilla, or Going to Bed book, or Pat the Bunny. That would just be too big to try and fit all of this on one slide. So I apologize for not showing you the complete tree. But once we put the alphabet room on the shelf first, we could take this path and do Goodnight Gorilla and Going to Bed book and Pat the Bunny. That's why these are labeled 1, 2, 3, 4. Or we could take a slightly different path. 1, 2, 3, 4. If the second one was the Going to Bed book, we could take this path, or we could take that path, and so on. Does that tree make sense to you? And you see why you need a different tree if you had a different first book. I just don't want to try and draw all of that. So we had 6 different paths. 1, 2, 3, 4, 5, 6. Starting with this book, there were 4 ways to start the first book. So 6 times 4 is 24 different ways to do things. We multiplied by decreasing numbers. 4 ways to put the first book on, 3 ways to put the second, 2 ways to put the third, and then the last book we just stick on. There's no more choices. Why did we multiply by that list of decreasing numbers? Because the number of options we had each time goes down by 1 when there's 1 less book, because it's on the shelf. Everyone okay with that example? Tangentially, it doesn't have to be 4 different toddler books. They could be 4 of anything. And if you ask me how many different orders could I put them in, it's going to be 24. Whether it's 4 different pieces of music that a musician performs at a recital, or 4 different ways that I can line kids up at recess to be a team of 4, or whatever it is. If I'm arranging 4 things, it's exactly the same. The first item, I have 4 ways to put it first. Then for my second choice, I have 3 things left to choose among. Then I have two things left, and then the last one I just put at the end. Okay. Hold on to your heads, more jargon, then we will rest our brains. We will definitely do lots of example problems of this. This is like the crux of what's hard in probability. So I will show it to you now, and we will spend lots more time looking at this in the next few days. We need more words to talk about this carefully. An arrangement is the kind of thing we just did, a possible way to place items from a group. Arrangements do not allow repetition. Once we put an item in its place, it stays there. We can't pick it up and use it again. But there are two things to ask about arrangements. First, do we place all of the items, or do we just put some of them on the shelf and then stop? Maybe there's a deal with pizzas. You get to pick any 3 pizza toppings for your special large pizza on sale. But the restaurant has 12 different toppings. So we're only going to pick 3 of them and then we stop. We're not putting all 12 toppings on our pizza. Other times, like putting away books on the shelf, you normally do all of them. You don't stop halfway through. We can also ask, after we're done, do we care about the order of things? If we do, we say the arrangement is ordered. Maybe I really think doing 4 different pieces of music at my recital, it matters what order I do them in. If we don't, then we say it's unordered. If I'm picking 3 pizza toppings out of 12, I don't care which order you list them in. The pizza will be the same either way. So this chart will be your wonderful thing. I'm going to see if I can take the formula page that we have and fit it in the bottom right corner, maybe scoot things around a little. But this will be the probabilities version of our formulas. So I'm not going to look at this chart right now. This is the summary of what comes later. If I tried to talk about this chart right now, I would hurt your brain. Let's look at things one at a time, and then we'll come back and see how they're all on the chart once we've talked about them. The chart is at the top just because when you use it as a reference, you'll want it to be before everything, not a conclusion at the end. But for the first time you see it, skip the chart. Okay, I'm also going to make this bigger. I can't believe you that the font is big enough. So we had an arrangement, meaning we don't get to put things back. And if it is ordered and uses all our items, we call it a complete permutation, like putting away books in the library shelf. All the books get put away, and in a library, the order does matter. One order would make the librarian happy. Any other order probably would not make the librarian happy. When we're looking at the toddler books, we already saw this pattern. We multiply, starting by with the number of items, and we decrease by 1 each time. And this happens because the active sample space decreases by 1 each time we put something in the arrangement. So this pattern happens often enough that mathematicians have given it a name, a symbol, and even a calculator button. It's named factorial, and the symbol is an exclamation mark. So what we saw already was called 4 factorial, 4 times 3 times 2 times 1. That should be 24. Let me fix that real quick. Sorry about that. Okay, there we go. As another example, 5 factorial, that's going to be 24 times 5 now. So 120. This must have been too late at night. Okay, and then when I multiply by 6, I get to 720. Okay, there we go. So 5 factorial would be 5 times 4 times 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2, and so on. In general, we could write this as n factorial. It's just starting at n, multiplying by the numbers less than n, counting down until you get to 1, and then you stop. The times 1 actually you can leave off, right? Times 1 doesn't change anything. Okay, see if you understand this. The Gumball machine has 4 colors. There's only 1 gumball remaining of each color. The chance of getting any color is equally likely. So what's the chance that you get red, then blue, then pink, then green? How many ways were there to do 4 colors?
Twenty-four. Still.
Yeah, any complete permutation with 4 things, like those books, is 4 times 3 times 2 times 1, which is 24. So what's the chance of getting the particular one that's red, blue, pink, green? Don't make this too hard. There's 24 things. What's the chance I get one of them?
Is there, what's the chance you get one of them? Wouldn't there be 24 chances you could get either of them?
You just lost me.
Yeah, I'm confused.
I want a
Is
certain.
it, oh, go ahead.
Yeah, you go.
Oh, I didn't know if it was 4 divided by 24.
Close. It's not 4 divided by 24. Let's start listing them. So we could have red, blue, pink, green. That's the one that we sort of have highlighted this time, right? We could have red, pink, blue, green. We could have green, pink, blue, red, and so on. So there's 24 of those. What's the chance that we just have that one?
So that would just be 1.
1 out of the 24.
Okay, that's what I originally thought. And then Okay.
Notice that in this question, it doesn't matter which arrangement I put in the question. I could have said, what's the chance of getting green, pink, blue, red? And it would still be 4%, right? It's just the chance of getting one thing out of 24.
And the chance is like a keyword, sort of?
Mhm.
Okay.
I could have used the word probability or likelihood or any of those synonyms for there's 24 things, they're equally likely. How often will one of them happen? So that's a complete permutation. We use the factorial to find the total number of arrangements and then maybe do some math with it because of a different question. Okay, compare and contrast. We'll keep going. By the way, secret links are all over the place. This one is the colorful history of gumballs. Okay, partial permutation. There can be an ordered arrangement, but only using some of the items. So we call it a partial permutation because we only use part of the collection of items. This is the pizza that has only a few of the many toppings on it. Or think of a contest with 3 winners. I'm sorry, it's not the pizza because this is ordered. So think of a contest where there are 3 winners, only some people will win, and the order matters, whether you're first or second or third. A partial permutation was called a variation in older literature. You don't need to know that, but it might be that some website or book you look at uses the word variation. They mean this. So we can think of a partial permutation as starting to make a complete permutation, but then we stop early. Imagine that the toddler put the alphabet room on the bookshelf and then good night, gorilla, and then decided enough of that, she wants to chew on the other 2 books. So we're just putting a few on and then stopping early. The multiplication for a partial permutation starts the same. There were 4 options for her, of which we only pictured the one with alphabet room. And then there were 3 options for what she does next. But then she quits putting books on the shelf and starts teething. She never gets to the times 2 times 1 part at the end of the factorial. Right? The gray area that's crossed out doesn't happen now. It's only a partial permutation. So there is a clever way to do this. We're going to use division of factorials. We're going to first write too much multiplication. We go all the way down the list. 4 times 3 times 2 times 1. And then we say, we only really want the 4 times 3, which is why I colored them green. The 2 times 1, that didn't happen. She never put those books on the shelf. She never made the 3rd choice or the 4th, not really a choice. So we'll divide them away. We'll divide by 2 times 1. The green stays, the red and the blue cancel each other out. Something divided by itself doesn't change things. So what do we have? We started with the n factorial. N is how many? 4 books were in her pile. And then we divide by n minus r. Where do we get that? It's how many we have, the n, but we only use r of them. So we have to divide by how many we didn't use, the n minus r. And this also happens enough that mathematicians give it a name and now 2 symbols and a button on the calculator. It's named n permute r. And the symbols are either NPR with subscripts or P parenthesis N comma R close parentheses, depending on whether you like parentheses or subscripts more. I'm going to use parentheses because they're much easier when typing web pages. So the way to permute only some items, when you have n items total but use only r of them, is n factorial divided by, and then do n minus r and find the factorial of that. So that seems like a lot, but it's really not. So let's just do this. So I'm going to start by saying the other example was a complete permutation. This one is a partial permutation. The permutation meant that the order matters. And the partial is that we only use R out of our N items. So a lock manufacturer sets its locks with a random 5-digit number. No digit is repeated. And that number is then printed on the back of the instruction manual before the lock is packaged. If you were to just take a random package from the store, what's the chance that your lock would be 1, 2, 3, 4, 5, 6? And just like before, it doesn't matter whether I pick this arrangement or a different one. All I'm saying is what's the chance of getting one arrangement out of all of the possible ones? So first question, how many arrangements are there?
$120.
Of 5 digits. And I'm not allowed to repeat them. So this is indeed the partial permutation. So I'm going to say that P of N comma R is N factorial divided by N minus R factorial. In this case, N is 10. There's 10 different digits, but I'm only using 5 of them. So it's going to be 10 factorial divided by 10 minus 5 is another 5 factorial. And now I have to figure out how do I actually do this. Maybe your calculator has a factorial button on it. If so, good for you. I am going to show you a secret that will be so much of something that makes you happy. If we go to our Desmos Calculator, you might not have noticed this. Everyone recognize this? The link is at the top of our website on every page. Let me just show you in case you don't remember. Calculator right there. There's a secret little thing here that says functions. So if I click on that, I could say, hey, what's the mean of these numbers? And it tells me the mean is 6. Or I could say, hey, what's the standard deviation of these numbers? And there's the standard deviation. So now that you've finished midterm 2, I'm going to show you your secret buttons. One of them is the NPR. They can't make the subscripts nice for some reason. I don't know why. But anyway, so we're wanting to find the 10, 5. And it tells us 30,240. We could also do it the long way. What is 10 factorial divided by 5 factorial? And it gives us the same thing, because that's what the formula does. So use this secret function button, or use the equivalent on your own calculator, if that's easier for you. This isn't hard math. The calculator is doing all the work. In any case, 30,240, I should write it down. So the chance that a particular one of these, any particular one of them happens, so that's going to be 1 divided by that. So 1 divided by, no. Next line. So 1 divided by my previous answer. Oh, weird standard deviation thing. If you haven't seen it, 10 to the negative 5 means scoots the decimal place 5 points to the left. So I'm going to take 3.3 and take that decimal place and move it 1, 2, 3, 4, 5. That's what this meant of 10 to the minus 5. Scientific notation, look it up if you care. You will not have to do this. Anyway, so what do we get? If we wanted to write it as a percent, that would be 0.0033%. Really small percent chance of it happening. Not a tenth of a percent, not 100th, but 0.003% of a percent. So good luck getting the lock that has the factory setting of any particular. Okay, and now we're 5 minutes after. We have unordered things to talk about. And then we have what happens if we do allow repetition. That's really quick. And that's all the different kinds of arrangements. Going back up to the top, this table, we have now seen, let me put this actually on the Jamboard so I can highlight on it better. What happens if your arrangement has n things and the order matters, but you use all of them? That was the complete permutation. There were n factorial possible ways. It was like putting books on the library shelf. You have to put all the books away. If they're ordered, but we only use some of them, that was the partial permutation. We wrote it as P and R and permute R, like who earns first, second, third in a contest. And then there's the formula for that. So we'll talk about this side Wednesday. Okay, I'm going to stop recording.